Okay, today we are going to problem 6 and problem 14. Starting from the general expression 9.2 for magnetic vector potential A and the corresponding expression for electric scalar potential phi. Expand both are equal absolute value of the difference x minus x prime and t prime equal t minus r over c to first order in x over r to obtain the electric dipole potentials for arbitrary time variation, where p retarded is p of t prime equal t minus r over c is the dipole moment evaluated at the retarded time measured from the origin. The scalar potential is given by Formula 1. We use the expansion. So t prime equal t retarded plus n dot x prime over c, where t retarded is t minus r over c. Since rho is a function of t prime, we make the expansion rho of x prime t prime equal rho of x prime t retarded plus n dot x prime over c, partial rho of x prime t retarded by partial t plus dot 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 equal rho retarded plus n dot x prime over c partial rho retarded partial t plus dot dot dot. Then Formula 1 is expanded as 1 over 4 pi epsilon 0 r times total charge plus n dot 1 over r rho retarded plus 1 over c partial rho retarded partial t, where the expressions for charge and electric dipole moment are rho retarded equal x prime rho retarded integral over the space. By charge conservation, total charge is independent of time, so the subscript q retarded is superfluous, dropping the static Coulomb potential, which does not radiate, then gives Formula 2. We only need to keep the lowest order behavior for the vector potential. So the vector potential A of x equal rho 0 over 4 pi r, current density retarded, integral over space. Using the integration by parts, we have the relation. Therefore, the vector potential can be written down as Formula 3. So the problem A is done. Calculation the dipole electric and magnetic fields directly from these potentials and show that below. We use B field equal curl A to obtain the magnetic field, where the vector potential is given by Formula 3. Note that the electric dipole, rho retarded in Formula 3, is a function of the retarded time. By the chain rule, we have partial rho retarded partial r equal minus 1 over c partial rho retarded partial t. Since gradient r equal n hat, the magnetic field becomes to Formula 4. Problem C. Show how you can go back and forth between these results and the harmonic fields of 9.18 by the substitutions minus I omega to partial t and p exponential ikr minus I omega t to p retarded of T prime. With the substitution, the magnetic field, formula 4, becomes, and the electric field, formula 5, becomes. To go in the other direction, we simply read these equations backwards. So, the problem 6 is totally finished. Problem 14. An antenna consists of a circular loop of wire of radius A, located in the xy plane with its center at the origin. The current in the wire is I equal I0 cosine omega t. Problem A. Find the expressions for EH in the radiation zone without approximations as to the magnitude of Ka. Determine the power radiated per unit solid angle. Okay, since we have the current I and its distribution, so we can write down the current density of position. 1 over A times I of t delta r minus a delta cosine theta phi hat. A is a normalization factor determined by the integration. The integration has to be I. Use Jackson 9.149. We get the normalization factor A of electric field and the magnetic field, like this. Because R dot J has to be 0, therefore, all the normalization factor for electric field are 0. And the term can be write as sin phi times partial cosine theta times J by azimuthal symmetry. M has to be 0. So, normalization factor A for magnetic field can be sorted as this. And where this term equals to 0 when L is even. Therefore, from Jackson 8149 and 9.151, we can find the dp over the omega. So the problem A is solved. Problem B. What is the lowest non-vanishing multiple moment? QLM or MLM? Evaluate this moment in the limit Ka much less than 1. Okay, first, we have known that normalization factor A for electric field R have to be 0. So, the lowest non-vanishing multiple moment must be M10. And then with the limit Ka much less than 1, we have the relation of Bessel function. Here, this J1 of Ka equal Ka over 3, and this equal to root 3 over 4 pi. We substitute into the AM10, then we get the result Ik 3 over 3 times root 2 and 10 equal equal to I2 I times 2 pi k3 I0 a squared root of 1 over 1 of 24 pi. So the lowest non-vanishing multiple moment M10 equal root 3 over 4 pi times I0 pi a squared. Okay, so the problem B is finished.